Okay, these next three are absolute value equations, and this maybe was worth going over the key idea that you need to solve these. If I have some variable a and I take its absolute value and it equals something, you can look at this expression here and know that there's two different expressions for a that will make this work. A can either be 3, which is just what we see on the outside, but a can also equal the opposite of 3, because when we take the absolute value, it returns positive, so the absolute value of a in this case would be 3. So that's the key idea, is that we take whatever's inside the absolute value expression and we set it equal to what's outside of it, and then we also set it equal to the opposite of what's outside of it, and that's what gives us the two solutions. If you think about an absolute value graph, it's a V, and so kind of like in a parabola situation, we also get two solutions, and that's graphically what's going on when we find those two solutions. It's where the V intersects that x-axis when it happens. Okay, so this first one, just like usual, we're trying to get x initially by itself. So x is inside the absolute value, so in order to get that absolute value expression by itself, we're going to add 2 to both sides. We're going to get the absolute value of x equals 5. And then we're going to use that property I just talked about. The absolute value of x is going to either equal 5 or x will equal the opposite of 5. And in this case, we don't need to continue simplifying. Those are the two answers. And it says with absolute value equations, we actually need to go ahead and check our solutions. So let's go ahead and do that. The first one, we have absolute value of 5 minus 2 question mark equals 3. So absolute value of 5 is just 5 minus 2 equals 3. 3 does equal 3, so that one works. Let's plug negative 5 in. Absolute value of negative 5 minus 2 equals 3. Absolute value of negative 5 is just 5 minus 2 equals 3, so 3 equals 3. That one works. Number 20, we have an expression inside the absolute value sign and it equals 7. So we're going to use the same idea here. We're going to take whatever that thing is inside the absolute value expression, set it equal to 7. 2x minus 5 equals 7. And then whatever's inside that absolute value can equal the opposite of 7. And then in this case, we need to go ahead and solve these little mini equations for x. So here we're going to add 5 to both sides. 2x equals 12. Divide both sides by 2, we get x equals 6. And here we're going to add 5 to both sides again. 2x equals negative 2. X will be, if I divide both sides by 2, x is equal to negative 1. And then we need to plug these back in to make sure they work. So the first one is 2 times 6 minus 5. That whole thing absolute valued. Does that equal 7? 2 times 6 is 12. Remember, with absolute values, you treat it like a parenthesis. So you have to do everything inside the absolute value before you apply the absolute value itself. So 12 minus 5, absolute value equals 7. 12 minus 5 is 7. So the absolute value of 7 does equal 7. So this one works. And then here we have 2 times negative 1 minus 5, all absolute value. Does that equal 7? 2 times negative 1 is negative 2 minus 5. Does that equal 7? We have negative 2 minus 5 is negative 7. Well, the absolute value of 7, negative 7, is 7. So 7 equals 7. So both of these solutions also work. Here I thought I'd just show you the graph of that absolute value equation we just solved. It's 2x minus 5, and then I have to put the minus 7 on the other side to graph it as a function. You can see that here are those two answers we found, negative 1 and 6. And so this is just a graphic depiction of what was going on with that last problem. Okay, 21. Same idea. We have the absolute value isolated by itself on the left here, so we just have to do our whatever's inside the absolute value equals what's outside, or what's inside the absolute value equals the opposite of what's outside. And when I do opposite, make sure you have to negate the entire expression here. So that's why I put it in parentheses. And then we're going to solve these little equations. Subtract x from both sides, subtract 1 from both sides, get -5 on the left, -1 minus 1 is 0, 2x minus x is just x, and so we'll get x is -5, but we'll need to check that out. And then here we have x minus 4 equals, now I got to distribute that negative sign, -2x minus 1. Add 3 to both. Oops, sorry. Going to add 2x to both sides to get rid of the 2x on that side. And then we'll add 4 to both sides here. So we'll get 3x on the left equals 3. Divide both sides by 3 to get x equals 1. Now we need to check these expressions. So the first one is -5 minus 4. Does that equal 2 times -5 plus 1? -5 minus 4 is -9. We have 2 times -5 is -10 plus 1. Absolute value of -9, does that equal -9? Well, no. The absolute value of 9 actually equals 9, which does not equal -9. So we have to throw that solution out. X equals -5 is an extraneous solution. This one, x equals 1, 1 minus 4, absolute value. Does that equal 2 times 1 plus 1? 1 minus 4, absolute value. Oops, wait. 1 minus 4 is -3, so that's in our absolute value sign. Does that equal 2 times 1 is 2 plus 1 is 3? Well, the absolute value of -3 is 3, and since 3 does equal 3, that question, or that solution works. So x equals 1 is our only solution. Here I've graphed number 21, which is actually more complicated than a straightforward absolute value graph. You see there's no v. It's actually like 2 lines with a kink down here. But I thought it'd still be interesting to show you that the only place it intersects the x-axis there is at 1, 0. So that other extraneous solution, x equals -5, if I go over to -5, it does not cross the x-axis right there. Oops. So another way to just graphically show that what we came up with is the right solution.